Imagine, if you will, a remote corner of the vast Sahara Desert.
Mm-hmm.
It's not just endless sand, though there's plenty of that.
Mm.
No. Picture mysterious chunks of brilliant yellow-green glass just scattered everywhere.
Really unusual stuff.
What's truly wild is that the ancient Egyptians knew about this material for millennia. They even incorporated it into their most precious jewelry, famously a beautiful scarab on Tutankhamun's necklace.
Right, that scarab is key.
But despite this ancient knowledge, this desert glass has remained, well, a profound scientific mystery. How did it get there? How was it made?
Yeah.
Today we're going on a deep dive to unpack how scientists are now linking this unique glass to a devastating ancient explosion, a type of catastrophe that could, surprisingly, happen again.
It's a fascinating scientific enigma precisely because it's so unique. I mean, its exact formation process has eluded us for so long.
Right.
But this desert glass, it's undeniably a natural phenomenon, which means, it demands a natural explanation. It might be an unusual event, certainly, but it's absolutely not a mystery that can't be solved.
So, okay, picture this. 1998, an Italian scientist, Vincenzo D'Indicò, he's at the Egyptian Museum in Cairo looking at ancient gems.
Okay.
He zeroes in on a piece of jewelry in a dark corner. A necklace with a carved yellow-green scarab right at its center.
The Tutankhamun piece.
That's the one. And this scarab was thought to be made of chalcedony, a pretty common semi-precious stone, sort of like chalcedony or quartz.
Standard stuff, yeah.
But Desmichel had a hunch. Something felt off. So under the watchful eyes of armed guards and museum officials, with the help of local geologist Ali Barakat, Desmichel was allowed to examine and test the jewel.
High-stakes testing.
Totally. He used a refractometer. That's a device that measures how light bends as it passes through a material, giving, crucial clues to its composition.
Its optical properties.
And the aha moment. The test revealed Desmichel was absolutely right. The scarab wasn't a semi-precious stone at all. It was unequivocally glass.
Glass, not stone.
And not just any glass. This was not a glass like any other produced by the ancient Egyptians. Yeah. Its color, its purity, everything about it set it apart.
This convinced Desmichel it wasn't man-made.
And that's what truly intrigued scientists, why this material was so puzzling. These desert glasses possess a color and this pure silica composition that make them genuinely unique in the world.
Pure silica.
Yeah, very pure. We know of no other natural glasses that look quite like this or have this precise composition. Most natural glass, as you probably know, is volcanic.
Right, like obsidian.
Exactly. Formed when hot molten magma solidifies rapidly, often by meeting cold water. But volcanic glass is quite different in its chemical makeup, and it's typically dark color.
Okay.
Another way natural glass can form is from a meteorite impact. You get immense temperature, pressure, and really rapid cooling that turns the ground into glass.
Impactites, right.
Impactites, or sometimes tektites. But again, these impact glasses, they're also very different in appearance, shape, and size from this desert glass.
So it didn't fit any known category easily? Not at all. For years, there was even this intriguing theory that the glass formed slowly at low temperatures, maybe in some kind of ancient swamp that dried up.
A swamp in the Sahara. That sounds unlikely.
It does now, but it was seriously considered for a while.
Okay.
Until it was tested.
And that low-temperature swamp theory, it turns out, was rigorously tested and ultimately, debunked.
Completely.
Christian Kobrel, a geochemist, decided to analyze the glass to establish, at what temperature it had actually formed. He went to the Natural History Museum in Vienna and used an electron microscope to examine the desert glass for a mineral called zircon.
Ah, zircon. Very useful.
Now, zircon is remarkably stable, but it's like a scientific thermometer.
Yeah.
It starts to break down at extremely high temperatures.
It has a known decomposition point.
Okay, let's unpack this a bit. Kobrel looked for changes in the zircon crystals specifically, these dark patches where the zircon had started to decompose, leaving behind more silica.
The breakdown product.
This partial decomposition was the key. It told him the zircon had been subjected to, but not completely obliterated by, immense heat.
So it got hot, but not so hot it vanished entirely.
Exactly. And what Kobrel discovered was truly mind-boggling. Temperatures around 1800 degrees Celsius. That's nearly 300 degrees Fahrenheit.
Whoa! That's incredibly hot.
To put that in perspective, volcanic lava barely hits 1100 degrees C, or around 2,000 degrees Fahrenheit.
Yeah.
This was a whole different league of heat.
Much, much hotter. Phenomenal heat, yeah.
Yeah.
Suggesting something far more extreme than, well, anything previously imagined for Earth's surface activities like volcanoes.
So what does this all mean then?
Well, it changes the game.
This finding completely forced scientists to consider an extraterrestrial explanation. It had to be a meteorite impact, right?
That became the leading theory, yes. That kind of temperature points strongly towards an impact event.
So with this astonishing temperature reading pointing squarely to an extraterrestrial impact, the scientific hunt for the glass's origin moved from the lab to the heart of the Sahara itself.
Out into the field.
A new team, including physicist Mark Boslaw, it was his first time in this desert, and the familiar faces of geologist Ali Barakat and geochemist Christian Kobrel, who were old desert hands.
Right. The veterans.
They set out on an incredibly challenging expedition to the Great Sand Sea. This is one of the most arid, inhospitable places on Earth. I mean, no one lives here. Rainfall can be absent for 10 to 20 years at a time.
Just brutal conditions.
It's a difficult 3-day drive through the desert before they can even start looking for glass. And you're driving on sand dunes that are themselves moving at an astonishing 10 yards a year.
Wow, constantly shifting landscape.
Which makes for treacherous driving.
Yeah.
And it's continuously uncovering new glass. One of the enduring mysteries about the glass is just the sheer scale. It's scattered over an area as big as Delaware,
Huge.
with estimates ranging from hundreds to maybe thousands of tons of this stuff.
Incredible amount.
Most of the glass lying on the surface is small and round, kind of sandblasted and polished by the wind over time.
Yeah, weathered.
But buried pieces are larger and rougher, often pitted and dull, etched by, whatever moisture gets down there over hundreds of thousands of years.
It's fascinating because even without an obvious crater right there, Ali Barakat found crucial microscopic evidence in the area.
Ah, okay. What did he find?
He and others discovered samples of sandstone where the quartz grains inside had these distinctive lines. We call them shock lamellae.
Shock lamellae?
Yes, they're basically microscopic fractures caused by the extreme pressure waves from an impact. You really only get them from hypervelocity impacts.
So undeniable proof of impact pressure.
It truly solidified the meteorite theory for many, yes. That was strong physical evidence.
So Ali Barakat finds these shock waves in the sand, undeniable proof of an impact. But wait, if there was such a massive impact, a heat so intense it melted the desert, why on earth wasn't there an enormous crater to mark the spot? That seems like the most obvious piece of evidence.
You've hit on the big one, absolutely. That was the major puzzle that stumped researchers for quite a while. That missing crater was indeed the obvious problem.
So how did they tackle that?
Well, Christian Kobrel was determined to find definitive extraterrestrial evidence within the glass itself, even without a visible crater. He headed back to his lab in Vienna.
Okay.
By bombarding black streaks, they found within some glass samples with neutrons a technique called neutron activation analysis. He found small traces of the exotic element iridium.
Iridium, right, the meteorite signature.
Exactly. It's incredibly rare on Earth's surface, but a telltale sign of meteorites. We wouldn't expect to find it in normal surface rocks.
But that wasn't the smoking gun yet.
It was strong evidence, but the true eureka moment came after over a year of painstaking searching. He found the rare element osmium.
Osmium?
Yes, and not only was its abundance 50 to 100 times higher than anything we'd ever find on the surface of the Earth, but its unique atomic fingerprint. Its isotopic ratios were unmistakably from space.
Wow. So different isotopes of osmium in proportions you only find in meteorites.
Precisely. That was the undeniable proof. It had to be a meteorite impact.
Okay, so the impact is confirmed by the elements in the glass. But what about the crater? What was Kobrel's explanation then?
His explanation, and it's a plausible one, is that it's probably a very deeply eroded structure. He points out that really old craters, like one in Chad that's over 200 million years old, can become extremely difficult to detect over geological time. Erosion, sand coverage. They can basically vanish from easy view.
So even with proof of an extraterrestrial impact, a deeply eroded structure. For something that powerful, it's still hard to imagine it just vanishing, Was that a theory the whole team immediately bought into, or is there still some skepticism?
Oh, there was definitely still skepticism. It certainly wasn't an easy sell for everyone, and that's precisely why they turned to remote sensing scientist Farouk Elbaz.
The satellite imagery expert.
Exactly. He interprets satellite pictures of Earth looking for geological features.
Right. And to help Elbaz in his search, they first needed to date the glass accurately. How do they do that?
They used a technique based on the decay rate of uranium isotopes within the glass. The team calculated the glass was formed nearly 30 million years ago.
30 million years, okay.
And Elbaz was convinced that a crater 20 to 30 million years old should still be visible from space, citing that 200 million year old crater in Chad as an example. If that one's visible, this one should be too, right?
Makes sense. So what did the satellites show?
Well, the satellite search yielded inconclusive results, unfortunately. While some circular features, potential craters, were found in the wider region, nothing was located right in the direct zone of the glass distribution.
Nothing definitive.
No, they had not really found the smoking gun crater for the silica glass. Elbaz did spot one interesting circular formation about 60 miles away that he thought deserved a closer look on the ground. But the rest of the team remained doubtful that this was the source. It seemed too far away, maybe unrelated.
So if there was no crater, what else could possibly explain the enormously powerful cosmic event that happened there nearly 30 million years ago?
This is where Mark Boslow's theory comes in, right?
Exactly. This is where things take another fascinating turn.
And it started with a catastrophic event, not in the desert, but way up in a remote part of Siberia. The Tunguska event in 1908.
Ah, yes, Tunguska.
A classic mystery.
A Russian scientific expedition finally visited Tunguska in 1927 to investigate. They were just astounded by the devastation. The blast had destroyed more than 80 million trees over a huge area.
Flattened them like matchsticks.
Yet they couldn't find a crater. Not a single impact crater. And no meteorite fragments either. For years, it remained a scientific mystery.
Baffling.
The commonly held belief became that an extraterrestrial object, maybe a small asteroid or a piece of a comet, exploded about 5 miles up in the atmosphere. This aerial burst
An airburst, yeah.
would have been equivalent to something like 20 million tons of TNT.
Yeah.
Over 1,000 times bigger than the atomic bomb dropped on Hiroshima.
Just a colossal explosion in the sky.
Which brings us to another place where an explosion created a layer of glass. The Trinity site in New Mexico. This was where the world's first atomic bomb was detonated in 1945.
A man-made comparison point.
Right. Sergeant Benjamin was part of the official photographic team. He described the explosion as incredibly bright, 20 times the brightness of the noonday sun. And then this blast of heat felt like opening the door of a furnace.
Intense thermal radiation.
A week later, he returned to ground zero. The steel tower the device was on, absolutely vaporized, gone. And the ground, he said, it was covered with green glass, the melted sand here. This green glass was covering the whole entire area. He described it like walking on a field of slick green ice.
Trinitite, they call it. Melted sand from the blast heat.
Exactly. Now, the Trinity glass area was about 600 yards wide. But the Sahara glass area, it's thousands of times larger.
Immensely larger.
So you'd need, I don't know, many thousands of atomic blasts to produce that much glass.
The scale is just completely different, which points back to something far, far more powerful than Trinity.
And this is where Boslow's expertise in computer simulations of large impacts comes into play.
Yes. Mark Boslow specializes in modeling these kinds of events.
The real turning point in understanding these atmospheric impacts was the collision of Comet Shoemaker-Levy 9 with Jupiter back in 1994, wasn't it?
Absolutely pivotal. That event changed everything. The comet broke into over 20 fragments.
A string of pearls, they called it.
Right. Which then, one by one, slammed into Jupiter's atmosphere over several days. Boslow's team developed simulations that predicted massive fireballs and plumes rising high above the cloud tops.
Yeah.
And when the Hubble Space Telescope images came in, they were spectacularly confirmed. Huge, dark scars, massive plumes, just like the models predicted.
Wow. So the models worked for Jupiter.
They did. And this is a key moment. The lesson learned was that impacts don't just create craters. The planet's atmosphere plays a tremendously important role in how the energy is deposited.
Okay, so the atmosphere matters. How does that connect back to the desert glass?
Well, another scientist, John Wasson, one of the world's top meteorite experts, was also paying close attention. He was particularly interested in a specific type of desert glass sample.
What was special about it?
It had very distinct layers. Some dense, bubble-free glass and some foamy glass just full of tiny bubbles.
Layers. Interesting.
Wasson theorized these layers were formed by intense heat radiating from above, from an extremely hot sky, basically, not from an impact shock wave hitting the ground directly.
Heat from the sky.
And this immediately brought the Tunguska event to mind for him, an airburst.
Okay, I see the connection.
So if we connect this to the bigger picture, Wasson and Boslow started to wonder, could a similar but much, much larger aerial burst have happened over Egypt 30 million years ago?
A super Tunguska event.
Essentially, yes.
So To test this bold aerial burst theory, Boslow adapted his computer model, the one validated by Shoemaker-Levy 9, using the latest data from the Sahara, the glass properties, the estimated energy needed.
Right, feeding in the constraints from the actual site.
The simulation modeled a 120-meter diameter object, about the size of a football field, entering the atmosphere at something like 20 kilometers per second. Incredible speed.
That's hypersonic, yes.
Describe for us what that simulation showed happening. What did it look like virtually?
Well, the powerful visuals of the simulation showed the meteorite entering the atmosphere and starting to break up and burn intensely. It leaves this incandescent trail of material in its wake, a massive column of fire, which then collapses downwards and outwards, turning into a huge fireball.
Okay, a fireball.
Yeah.
But how does that make glass on the ground without a crater?
This is the crucial part. The simulation showed the fireball doesn't just dissipate upwards. It gets pinned against the surface by its own downward momentum and the atmospheric pressure.
Pinned to the ground.
Yeah, and it's moving incredibly rapidly across the landscape, well beyond hurricane force winds. But it's not just wind, it's essentially a blast of superheated air that's hotter than the melting temperature of sand blowing across the desert surface.
Like a giant blowtorch from the sky.
Exactly like that. This searing hot air melts the top surface layer of the sand, which then cools and freezes almost instantly behind the shock front to form the sheets of glass.
Wow. So it melts the surface in place.
Precisely. And just like they saw on Jupiter, the simulation also showed an enormous plume of the searing gas and vaporized meteorite material streaming back out into space.
And the scale of this simulated event?
Yeah.
Compare it to Trinity again.
Oh, it's hugely bigger in energy, hugely more powerful. The simulation suggested an energy release maybe 10,000 times more powerful than the atomic test at Trinity.
10,000 times. That explains the huge area of glass. So what's the final verdict from Wasson and Boslaw? Do they think this simulation solves it?
They now believe they've solved the mystery, yes. 30 million years ago, an asteroid on a collision course with Earth, headed for what is now Egypt, broke up high in the atmosphere in a catastrophic aerial explosion.
It didn't hit the ground intact.
Right. It created this blistering, ground-hugging fireball that radiated intense heat downwards, melting the sandstone surface and turning it into the distinctive yellow-green Libyan desert glass. No crater needed.
That is an incredible picture. It really ties everything together. The glass, the heat, the lack of a crater.
It seems to fit all the evidence remarkably well.
So this discovery brings the implications of these cosmic events squarely into the present. It seems the theory predicts that aerial explosions are far more likely if the object breaks up easily, like that fragile comet Shoemaker-Levy you mentioned. But why would that be the case for asteroids generally? Aren't they solid rock?
Well, that used to be the common assumption, but there was a real paradigm shift in understanding asteroids back in 1997. A NASA spacecraft near Shoemaker flew by an asteroid called Mathilde. And by measuring its mass and volume, they calculated its density. It was surprisingly low. Mathilde's slow rotation also suggested it wasn't a solid, spinning body. The conclusion was startling. It wasn't solid rock, but more like a flying rubble pile, a loose assembly of rocks and boulders held together mainly by their own weak gravity.
A rubble pile.
Yeah.
Seriously. Like a bag of gravel flying through space.
Pretty much. And it's now believed that most asteroids, especially the larger ones, probably consist of these rubble piles. They're structurally extremely weak.
Which means
they are very likely to disintegrate and explode violently if they enter Earth's dense atmosphere at high speed. They just can't handle the aerodynamic stress.
So it's not just a theoretical possibility. We have evidence of this happening elsewhere, not just in the Sahara 30 million years ago.
Absolutely. John Wasson, the same scientist who studied the layered glass, believes he has evidence of another super Tunguska-like event, maybe even bigger, from about 800,000 years ago.
Where was this?
He's found tektites, a type of impact glass scattered all over Southeast Asia. Thailand, Cambodia, Laos, Vietnam, even southern China. It's called the Australasian strewn field.
And again, no crater.
Again, no convincingly associated crater has been found, despite decades of searching. The area covered by the glass is enormous, some 300,000 square miles.
Wow.
Wasson's interpretation is that a large rubble pile asteroid broke up over the region, its fragments becoming multiple fireballs that incinerated everything on the ground below.
That's terrifying. Which leads us to wonder, how do we protect Earth from such a phenomenon if these things explode in the air?
That's the critical question, isn't it? And Hollywood's usual cinematic solutions for asteroid defense, like blowing them up just before they hit, well, it turns out those are entirely off base.
Why? Wouldn't breaking it up help?
Actually, no. Exploding a rubble pile asteroid just before it hits Earth, especially if it's already close, would probably make the situation much worse.
Worse.
Because instead of one impactor, you'd create a shotgun blast, a lot more smaller pieces hitting the Earth over a wider area, and potentially they're all large enough to create dangerous fireballs. You'd spread the destruction.
Right. Multiple Tunguskas instead of one maybe survivable splash. Okay, so blowing them up isn't the answer. How often do these things happen?
Well, luckily, the really large asteroid collisions, the potential extinction level events, happen maybe millions of years apart. And astronomers are actively tracking those bigger threats, the kilometer-sized objects.
Okay, that's somewhat reassuring.
But these smaller Tunguska-like events caused by objects maybe tens of meters across, those could happen much more frequently. Estimates range, but perhaps as often as once every 100 years or so, somewhere on Earth.
Every 100 years, that's
Yeah.
quite often, geologically speaking.
It is, and the challenge is these smaller objects are much, much harder to spot with current telescope surveys. They're faint, and they could come from unexpected directions. Often, there would likely be no warning at all before impact.
No warning.
So, while the probability of one hitting a populated area in any given century is statistically small, it's certainly not negligible. It really could happen in our lifetime.
And the consequences.
If it hit in the wrong place, over a major city, it could be absolutely devastating, potentially killing millions of people. Remember, the devastation from even the relatively small Tunguska fireball extended over an area about 8 miles wide.
An 8-mile wide zone of destruction.
Yeah.
From an airburst.
Yes, and we now know what happened in the Egyptian desert 30 million years ago was even more destructive, created by a larger object. And the physics hasn't changed. It will happen again.
And there are far more of these smaller ones out there.
Hundreds of times more of these smaller city-threatening asteroids than there are of the big ones that the astronomers track diligently. So yes, there will be another impact on the Earth. It really is just a matter of when.
So we've gone from a beautiful, mysterious scarab on an ancient Egyptian necklace all the way to a cosmic event of unimaginable power, finally revealed through decades of, well, really cutting-edge science and some clever detective work.
It's been quite a journey of discovery.
The Sahara Desert glass isn't just a relic of the past. It's a profound testament to a powerful, often hidden force from space. It tells us the very ground beneath our feet can hold secrets to ancient cosmic catastrophes. How does this new understanding of rubble pile asteroids and atmospheric impacts change your perception of Earth's vulnerability and maybe our place in the solar system?
It certainly makes you realize the atmosphere is both a shield and sometimes the medium for destruction itself.
What does it mean to live on a planet where such devastating events are not just ancient history buried in sand, but potentially a matter of when, not if, for the future? Something to think about.